Welcome. I wanted to say something quickly about finite topological spaces. I'm still working on the question to characterize within finite mathematics what homeomorphism is. So if you have a manifold like this or a manifold like that, they should be homeomorphic. I mean, if you have a finite topological space, I mean, these are classical notions of topological spaces. We can not use the classical notion of homeomorphism because that would mean the two spaces are really, you know, have the same cardinality. It's a bijection between the topological spaces, which is not really useful. First of all, it uses the smallest open sets which we have in a finite topological space. So these topological spaces have been studied early, like in 36 or 37. Kolmogorov and Alexandroff especially was looking at this. And then in the 60s there was more work on finite topological spaces, so in connection with homotopy. But it's an interesting question: how do you actually capture homeomorphism in a nice way? And the open sets are just the stars. These are the stars of this of a simplicial complex. For example, here this is a kind of a visualization of a simplicial complex, of an open set in a simplicial complex. You see there are no boundary points, and the boundary is here. That's sometimes called the link also, but I can put the boundary together, and then we have a closed, if I add the boundary, we have a closed set, which is the same than talking about simplicial complexes. So it's an interesting thing from a categorical point of view that you have three completely different things. Like we have topologies and we have graphs. I like graphs because they allow visualizations. And then we have simplicial complexes, which are finite set of sets closed under the operation of taking finite subsets. So these are all finite geometries, and each has an advantage. And we can go from one to the other. We are in a graph, we can get its simplicial complex, which is the set of complete subgraphs, and then we can from that get again a graph by taking the sets as the vertices and connect to if one is contained in the other. This produces again a simplicial complex, and so on. This produces barycentric refinements, and modulo barycentric refinement, it doesn't really matter what you are talking about, whether you're talking about finite topological spaces or whether you talk about finite graphs or whether you talk about finite simplicial complexes. So this has been realized, I think, in the 60s, right? If you have a topological space, it has the homotopy type of a simplicial complex. So that's just essentially these as complexes have, first of all, the simplicity. You know, there's just one axiom, and then there is also there are exterior derivatives, natural exterior derivative, and so we have a cohomology, and we can look at matrices, and we can use algebraic topology. Graphs have really the advantage that they can be visualized, they can be seen nicely. We have also a nice arithmetic in the form of a multiplication, a Shannon multiplication, and the disjoint union. So I currently think about, you know, what is a homeomorphism. I define it as a complex is a continuous image of another complex if there exists a continuous map, in the classical sense, continuous map from G to H, from this topological space to this topological space. But then we want also to have that every of these smallest units, these kind of Planck units, which you have, these stars, these are the stars which are the set of sets which contain, the star is defined here as the set of sets which contain a given set. And these are the open sets, these are the basis elements of the topology. And then we can look also at the closure minus the set itself. That's the boundary, classical notion of boundary, how you define the boundary. That's of course closed because the closure is closed and the complement of the open set is closed. So the intersection of the closure and the complement of the open sets, that's the boundary that's closed. And that's what I call the unit sphere, analog of the unit sphere. Sometimes one calls this a link, but only if the vertex has been a zero-dimensional point. We consider it for arbitrary points in the simplicial complex, of course. So this is how you, and then we want that this, of course, this open set gets mapped. This is -1 here. This open set, the inverse image of this open set is an open set, but we want this open set to be kind of like an open ball. So we want the boundary to be homeomorphic. That's an inductive assumption. We can then just reduce. So what I look at here are kind of three very, very simple examples. This is the simplest examples you can imagine. So first of all, we have the complete graph. Start with a complete graph with two elements. That's this graph here. So it has two vertices, one edge. So that's this one. And what happens is, so the simplicial complex has now three sets, right? The two vertices and then the edge. So these are the three sets. And then we can look at the topology. So the topology consists of all, as a base, all the stars. So the star of this element is everything which is contains this element. This is this. So that's one star, that's another star. And then there is this is the third star. This is all the simplices which contain only the simplex. Open sets. These are these three open sets. And then there is also the empty set. In any topology you have an empty set, and there is also the space itself. So there are 5 points in this topology. And so now what we can do is we can also take this simplicial complex and define a new graph. So when you take it a new graph, you make out of this edge, you make a vertex. So this is the new vertex which you have now, which was originally just an edge, and you connect two if one is contained in the other. And so now this is the Barycentric refinement which you have, and then you can do the same. So you can look at what are the open sets. For example, this is the star of this vertex. This is the star of this edge. The star of this vertex is this. This is the star. So this is an open set. The closure is this, and if you take the interior away, you end up with it. So this is another example. This is actually the zero sphere. The zero sphere is even simpler than that because it's zero dimensional. So this has only two vertices. This is the zero dimensional sphere. Why is it a sphere? Because we can take away one and then it's contractible. And the unit sphere also is a sphere. It's the empty complex. The empty complex is the -1 dimensional sphere. So this is we start here with this graph. So there are two vertices, no edges, and then we can form the simplicial complex. The simplicial complex has only two sets here. So in the simplicial complex there is never the empty set. And the empty set is not contained by definition in simplicial complex. empty set itself is a simplicial complex, but it also doesn't contain the empty set. And then we have the topology. So this topology has 1, 2, 3, 4 elements. This topological space has 4 elements. This topological space had 5 elements. Now, this is the skeleton complex of the complete graph, while this would visualize the complete graph. So we have to say that usually we assume that we take all the complete subgraphs, so that's what we usually assume. But in this case, we started with a simplicial complex which doesn't come from a graph. So this is not a Whitney complex of a graph, but it's still a simplicial complex. And then when we take the Barycentric refinement, if we kind of take this complex, we take all the sets which we have 6 sets, and we connect to if one is contained in the other. So we get now a larger simplicial complex, a larger graph, and six elements, and also a larger simplicial complex. And now in this complex, there are now much more elements already. I can compute that with a computer, how many elements there are. For example, this is an open set, it's a union of open sets. This is an open set because it's the star of an edge. As another example, the last example would be kind of here. We have a wheel graph. I start with a wheel graph, which is defines a two-dimensional complex. And then this defines has then a topology. Now, what are the possible open sets which you can look at? That's why it's sometimes maybe called. That's maybe why it's called a star. In this case, if we take this edge here, the star consists of all simplices which contain this one. So this is this. If we take an interior edge here, we have 2 triangles attached. These are, and then in this, that's the and X is the two-dimensional part, two-dimensional simplex. Then what we have is by itself, it's an open set. That's what I wanted to say. I'm just writing this down now and hope to finish this soon.